You open an app on your phone, type in a handle, enter an amount, and swipe to send. Within seconds, the money arrives. Traditional digital payments move through private, centralized databases. Crypto, however, relies on a globally synchronized ledger. Digital coins never physically travel through the internet. Your wallet broadcasts a message to a global network of computers, requesting an update to a shared public record. The request instructs the network to decrease the balance of the sender's address and increase the balance of the recipient's address by the same amount. Because no central bank exists to verify your identity, the network requires mathematical proof that you have the authority to request the specific state change. To gain approval, your request must survive a rigorous 6-stage decentralized execution pipeline, moving from a local cryptographic signature to an immutably confirmed update on the blockchain. This diagram maps the complete transaction pipeline. The process starts here, at stage 1, creation. When you initiate a transfer, your wallet acts as an isolated sandbox. It assembles a discrete data package entirely offline. It pulls together the sender's address, the recipient's address, the transfer amount, the proposed gas fee, and a sequential counter known as a nonce. Once compiled, your private key applies a unique cryptographic signature to the package, permanently sealing those variables inside. Anyone on the network can later use your derived public key to verify this signature. This mathematical relationship guarantees the authenticity of your request without ever exposing your private key. With the package sealed, the pipeline advances to stage 2, broadcast. Your wallet connects to a single network node and hands over the signed transaction. That receiving node duplicates the packet and passes it to its neighbors, who duplicate it and pass it to theirs, triggering an exponential ripple effect. Broadcasting in Web3 is not sending a message to a single authoritative server. It is the process of saturating a distributed network with copies of a cryptographic request. Those copies eventually pool in stage 3, the mempool. This is the public waiting room where unconfirmed transactions idle before processing. Processing these requests requires real computational work. If this bandwidth were completely free, malicious actors could paralyze the system by flooding it with infinite junk data. The solution is a fee structure called gas. By attaching a tangible cost to the computational effort required, spamming the network becomes economically unviable. The term originates from the Ethereum network, where executing complex smart contracts burns significantly more computational fuel than processing a simple transfer. Inside the mempool, this feed dictates priority. Validators are rational actors. When building the next block, they select the packets offering the highest gas fee. When demand for limited block space increases, users bid against each other, causing base gas fees to spike rapidly. During the peak of the NFT boom in May 2021, network congestion was so severe that Ethereum's mempool backed up entirely. Users routinely paid hundreds of dollars in fees just to jump the queue. Modern networks like Solana approach this differently. They utilize upfront rejection to fail underfunded transactions immediately, keeping them out of the queue entirely and saving users from pending limbo. Gas acts as a free market pricing mechanism designed specifically to protect the network's bandwidth and maintain its security. Once a validator selects your transaction, it enters stage 4, validation. Here, it faces strict automated protocol checks. First, the network verifies the cryptographic signature against your public key to ensure total authenticity. Next, it checks the ledger to confirm that the sending address holds the required funds. Finally, it scans the network to guarantee this specific transaction hasn't already been spent elsewhere. The rules are absolute. If a single check fails, the transaction is dropped silently. If all pass, it graduates to stage 5, block inclusion, compressing alongside hundreds of identical packets. This newly formed block is stamped with a unique mathematical identifier derived from its data. To cement its place, it must include a strict reference to the identifier of the preceding block, locking them together in a sequential chain. Through this cryptographic bundling, a localized user request is successfully transformed into a global consensus candidate. The final step is stage 6, confirmation. You receive your first official confirmation the exact moment your transaction's block is added to the chain. With every subsequent block built on top of yours, the computational difficulty of going back and altering your transaction increases exponentially. This interface shows a block explorer. It acts as a search engine for decentralized data. By pasting your unique transaction hash into the search bar, anyone can audit the exact execution of that request. The status field records the final outcome. Even if a transaction fails, it remains recorded on-chain, and the gas fee is consumed because the network successfully performed the computational work. The block and timestamp fields map the transaction's precise location in the chain, providing immutable proof of exactly when the execution occurred. The from and to fields display the raw wallet addresses. Because no names are attached by default, public ledgers are pseudonymous. The identities remain hidden, but the financial activity is totally transparent. The fee metrics break down the exact computational cost, contrasting the maximum gas limit you authorized against the actual gas consumed during the mempool market pricing. Finally, the nonce field reveals the wallet's internal counter, guaranteeing your transactions are executed in precise chronological order and preventing replay attacks. This absolute transparency creates a system where trust is no longer required to verify an outcome. A freelance developer in Lagos waiting on a cross-border payment does not need to rely on a bank's opaque routing updates. The transaction hash exists publicly, proving objectively that the funds were sent. Public blockchains bypass the closed databases of traditional finance, replacing them with an architecture built entirely on mathematically verifiable certainty.